Hello everyone, and welcome to our lecture on circularity in buildings with a focus on regenerative strategies. I'm Kyoung-Hee Kim, a professor of architecture at UNC Charlotte's School of Architecture. Today, we'll explore how the circular economy applies to building design and construction. In particular, we'll look at how we can move beyond the traditional reduce, reuse, recycle mindset to regenerate our resources and environments. This means designing buildings that not only minimize waste, but also actively give back, for example, by using renewable materials and integrating living systems. By the end of this talk, you'll see how regenerative design can help us achieve net zero waste and even improve our environment as we build. Let's talk about three approaches to using resources: linear, recycling, and circular. In a linear economy, we take raw materials, make a product, and then dispose of it as waste. This one-way model has dominated construction, but it's clearly unsustainable. A recycling economy improves this by processing waste into new materials, reducing disposal. However, recycling still often requires continuous inputs of virgin resources. A circular economy, by contrast, aims to close the loop entirely. Materials are kept in circulation through reuse, repair, and recycling, and biological resources are returned to the earth to regenerate nature. We can make buildings more circular by reusing and recycling more and wasting less at every scale. For example, instead of only recycling used materials, we can reuse building components, from individual elements like bricks or beams, to entire building systems and modules, and even whole buildings through adaptive reuse. As we move up from recycling to reusing larger parts of buildings, we retain more of the original value and require fewer new resources. With increasing circularity comes increasing benefits. Greater economic value is achieved through savings on material costs, and greater environmental value is realized by lowering carbon emissions and waste generation. The more we can reuse and repurpose in construction, the bigger the win for both the economy and the environment. Each step towards higher reuse is a step towards a true circular economy in the building industry. On this slide, we outline the circular economy framework as it relates to a net zero waste strategy in construction. Aiming for net zero waste means designing and building in a way that no materials go to waste during the building's life cycle. We implement this through four key approaches: reduce, reuse, recycle, and regenerate. Reduce means designing buildings to use fewer resources and generate less waste from the outset. Reuse is about designing buildings whose components can be easily disassembled and used again. Recycle involves processing discarded materials into new products, the focus of our discussion today. Regenerate enables building materials to replenish raw materials or restore ecosystem benefits. Additional videos on reduce, reuse, and recycle are available. One way to achieve net zero waste in the built environment is to use renewable bio-based materials that can be regrown and reabsorbed by nature. Wood is re-emerging as a major construction material in response to environmental stewardship. Buildings with wood can be a cost-effective and sustainable alternative that can have positive impacts on the environment, the economy, and our building culture at large. Timber from well-managed forests is also renewable, as the forest can be replanted and the supply is therefore sustainable. Certified wood products ensure their origin is sustainable and these woods can be traced. One example is FSC certification. Certified timber gives us confidence that we're not depleting forests. Moreover, timber components can traditionally be reused or recycled after a building's life cycle. Timber beams and columns can be remilled or incorporated into new structures. In a circular economy, timber emerges as a sustainable material because it stores carbon during a building's use and is either biodegradable or is reused, leaving behind minimal waste. We're at a turning point now where advanced engineered wood like glulam and CLT panels can replace steel and concrete in many structures, drastically reducing construction waste and their carbon footprint. Slides 7 through 11 showcase Hacine Cherifi Gymnasium in France. This modern gymnasium showcases regenerative design by using renewable materials like glue laminated timber and agri-waste insulation and minimizing waste. The glulam frames span 34 meters and are built in sections with bolted connections, illustrating design for disassembly. The column-free space meets the gymnasium's needs. The interior space is bright with clerestory windows and is well insulated, meaning less energy use. This slide shows structural construction. The portal frames are made of glulam structures. They were manufactured in a controlled environment and then assembled on-site with bolted connections. Off-site prefabrication contributes to circular construction because it improves quality and precision with less material waste during construction. Prefabricated components can fit perfectly and potentially be taken apart with less damage. Straw is an agricultural byproduct, essentially waste from farming. In this project, it is used as insulation for building enclosures. Using straw and wood fiber panels instead of synthetic insulation helps store carbon. These agricultural insulation products are biodegradable and low cost. At the end of their life cycle, they can decompose or be reused without harmful residue. The innovative use of agricultural waste or biomaterials aligns well with circular economy goals by utilizing locally sourced materials, repurposing waste, and reducing waste generation. Next, we have the Grandview Heights Aquatic Center in Surrey, British Columbia. This slide showcases a design concept of catenary structures where an undulating timber roof is naturally formed from its own gravity weight. A catenary is nature's blueprint for structural efficiency under gravity. The facility sits under the world's longest span timber catenary roof, an undulating wood structure that pushes the limits of timber strength while remaining remarkably thin. Structurally, slender glulam beams act as hanging wood cables between concrete buttresses, achieving a span of over 60 meters. The roof's curvature is made of glulam timber beams acting in tension, like timber cables. Using wood in this way was unprecedented. The design and engineering team thought they would need steel cables to support this sweeping form, but in a bold move, they realized that engineered wood alone could support the span. The roof is incredibly thin and material efficient as well. At only about 18 inches deep, including the wood decking, the roof uses far less material than a typical long-span roof would. Less material for the same function means less resource consumption overall. The large spanning structure creates a column-free space suited to the project's needs. The canopy appears to float above the water. The dynamic curves of the roof structure enhance spatial elegance and visual interest. The wood structure is treated to withstand the humid, chlorinated environment from swimming pools. It provides more natural warmth and acoustic comfort. The glass walls illuminate the space with daylight, highlighting warm wood surfaces and openness. Beyond aesthetics and engineering, the use of wood aligns with a local wood-first policy. The project leverages a renewable resource, Canada's abundant forests, to reduce the project's carbon footprint. Moving into emerging regenerative technology, this slide highlights some cutting-edge innovations that actively restore or replenish resources. The first example is microalgae biocement developed at the University of Colorado Boulder, commercialized by Prometheus Materials. Here, Living microalgae are used to create a new kind of cement that replaces traditional Portland cement, which is known to have a high environmental impact. This technology essentially grows building material in a low-energy process, offering a regenerative alternative to an otherwise polluting industry. Another intriguing idea is using photosynthetic bacteria to produce oxygen even beyond Earth. Scientists have proposed incorporating desert cyanobacteria into a living paint that could generate oxygen on Mars. Researchers at the University of Surrey created an oxygen-producing biocoating with these microbes, nicknamed green living paint. It was shown to steadily release oxygen while absorbing carbon dioxide in its environment. This has obvious appeal for extraterrestrial habitats, but it's also promising for Earth. Imagine building surfaces that actively refresh indoor air and sequester CO2. The paint's development illustrates regeneration at work, leveraging biology to continually renew air quality. Now we turn to a regenerative building system under development, a microalgae integrated facade, sometimes called a biochromic algae window. This system incorporates living microalgae into window systems or opaque wall applications. The algae multiply and generate a lipid-rich biomass. As the algae flourish, they sequester carbon, and we harvest the biomass to convert into biodiesel, literally growing a renewable fuel on the building's facade. As a concrete example of the regenerative technology, our team at UNC Charlotte and EcoClosure has been prototyping a microalgae window system that can yield biodiesel. Another regenerative material is plastic-eating mushrooms. Plastic-eating mushrooms break down plastic waste. In the context of a regenerative circular economy, fungi can serve as key agents of waste conversion. Certain fungal species can decompose persistent plastics like polyurethane, digesting polymers that would otherwise remain in landfills. Beyond breaking down waste, fungal mycelium can be cultivated as a biocomposite material for new applications. It can be engineered into compostable packaging or serve as a sustainable construction resource, for example, such as building bricks or insulation. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future through circular economy practices in the built environment.